share your screen whenever you're ready.
Yes. Okay. Can you see the talk?
I do.
Yes.
Yes.
Yeah, so should I go ahead? Yes.
Yes, please do.
Okay. Yes. Well, thank you everyone for being here. Welcome to my defense. I'm going to be talking about some quantum aspects of space-time geometry. So I've been studying space-time for the last 6 years, and I found it to remind me of this painting. Let me see if I can. Oh, let me make this smaller. Like that. Of this painting of Kandinsky that I used to see every day in Broira coming out of the elevator. As you explore space-time, you learn about several things. There are different corners for it to learn. You can learn about black holes, for example. You get to see about geometry or about how galaxies are formed. All of that is corners that we know from space-time. But there are also some other corners that are still unexplored, and it's been a lot of fun exploring some of these corners. One thing that I have learned is that the more you explore it, similar to the more you see this painting, the more mysterious but also fascinated it becomes. So in this talk, it's going to have 5 parts, mainly 3 reviews or introductions, and I'm going to be talking about 2 projects. So it's going to be 1/2 and 1/2. I'm going to start with a few basics of space-time. Okay, so the idea of space-time introduced by Albert Einstein in general relativity is that space and time are one entity together that is not rigid. It bends, it stretches, and it responds to matter. Matter dictates how space-time is going to stretch, and then gravity is nothing more than the effect of objects moving in space according to that curvature that is created. Something that is more fascinating is that not only space gets curved, it's the space-time itself. So time also can get stretched and bended, which means that some clocks generically are going to run at different rates. Here I have a picture of how planet Earth, for example, is bending the space-time. And the moon is just going to move around following that curvature. Now, this is a very fascinating thing to propose, but what are the real effects that we can see on daily? And one of the most surprising ones, I think, from our daily experiences is GPS. The global positioning system, it works the way that it works right now because we take into account the fact that we know that clocks that are farther away from the surface of Earth, they get time dilated. So, they run faster due to the being outside of the gravitational potential. So they go ahead of the clocks that are on the surface of planet Earth. And basically, if you know what is the distance at which these satellites are, and you can compute what is that time difference and how fast they are running in comparison to the clocks on Earth. And it turns out that they do it at 38 microseconds per day, which you might say, that's tiny. It's very hard for us to even imagine what this amount of time phase is. But in fact, for the GPS, which needs a lot of precision, accuracy, this accounts for an error that accumulates 10 kilometers per day. So next time you arrive at your destination using the GPS, you should thank general relativity that you didn't get lost for 10 kilometers or more. More surprisingly is that not only massive objects, they get different trajectories according to the curvature of space-time, but also massless objects. In this case, that means that light rays, photons, light rays, they also get bended. This is a prediction of general relativity according to how the space-time geometry. Here I'm showing a light ray, for example. If you have an emission of a light ray behind a big star like our sun, that light ray can get bended, and you will see from Earth that it's coming from a different location, even though it's coming from behind. That's another surprising effect of space-time. perhaps even more mysterious is the prediction of black holes, which usually we think of them as objects. I like to think of it as a region of space-time. And what happens is that as you start adding more and more dense, heavy objects in the space-time, you start with a sun, which is going to give a particular bending. You add something that is heavier, more compact, like a white dwarf, it's going to get even more bended. And if you do this to the limit where you're adding a lot of mass into one localized region, the space-time is going to get bended so much that you create this distortion that we call a black hole. Basically, what happens is that the bending is so large that there are regions inside that for you to escape, you will need to move at a speed that is larger than the speed of light. So since we know the speed of light provides a limit for the speeds in the universe, everything that falls inside is just doomed to be inside. Seth is going to be helping me muting some of this. Okay. Let me just get back to my, okay, so black holes, good. You might be more familiar with this picture that came out a few years ago. This is a picture from the Event Horizon Telescope, an array of radio antennas sparse just all throughout the surface of planet Earth that are looking at the center of galaxies, in this case, the galaxy M87, where there's a supermassive black hole, and they use the combined data that they observe to give us this picture. So this is a picture of a supermassive black hole. The feature is that there's a dark region in the middle, which has to do with the shadow that the black hole casts, because light rays that go directly into the black hole, they cannot escape from the other side. This is more tangible evidence. Okay, one of the most surprising, well, not surprising, but one of the aspects of space-time that now we are beginning to use more and more is that of gravitational waves. So I'm going to talk about that next. As I was saying, space-time, it gets bended, and it's good to have this picture of being more like of an elastic fabric that can get stretched and can get warped in different configurations. And as an elastic fabric, if there are some disturbances on it, you're going to generate some ripples that just go away. And these ripples of space-time is what we call gravitational waves. Now, to create very, what do I want to say? Sorry, never mind. This is a very real effect that was predicted by Einstein over a century ago, that in the same way that we see waves in the surface of water, we should also expect waves traveling through the space in the fabric of space-time itself. Now, this is a prediction 100 years ago, and it took another 100 years for them to be detected. The reason why it is so hard to detect them is that the disturbances that are created by objects, astronomical objects, when they collide, for example, are very minuscule, and it's really hard to detect them. So 6 years ago now, we had Advanced LIGO together with Virgo detecting the gravitational waves for the first time. These were the gravitational waves that were emitted with the merger, just the colliding, the collision, the merger of a pair of black holes of roughly 30 solar masses each, 36 and 29 solar masses is the estimate. And this was emitted 1.3 billion light years away from us, which means also that's more or less the time that it has been traveling until it reached planet Earth. Now the question is, given that this gravitational wave was emitted, how do we detect the gravitational wave here on Earth? And basically what happens when the ripple passes through the planet, if we imagine this being planet Earth, is that space-time itself is stretching in different directions. So as it goes through, the planet Earth is going to get stretched in one direction, get compressed in the other one, and then just oscillate as the ripple passes through. Now, not to worry, this is not how the real effect, I mean, this is not how really it gets bended. It's actually minuscule. It's very small, the deviation. And in fact, here I have the LIGO observatory. And to measure that really minuscule deviation, we need LIGO, which is a laser interferometer. So we need to use very precise lasers that are sent in two different directions, orthogonal to each other, for 4 kilometers and back. And when they come back, eventually we interfere them. And if there's any deviation in one of the sides, independent of the other one, you're going to see a change in the phase of the lasers. So you're going to see some constructive or destructive interference in the laser. And just for numbers, this is a 4 kilometer arms, and the difference in length is 1,000 of the width of a proton. So it's 10 to the minus 19 meters. It is minuscule. So we need a lot of precision to measure these gravitational waves. So far, after the announcement of the first detection, we have had 50 more detections in what it is now, I think, 2.5 observations. So hopefully in the next years, we're going to get more and more. And with each one of the new data, we're going to be exploring more aspects of general relativity and maybe deviations from general relativity. So how can we use this new piece of data, the gravitational waves, to explore spacetime? So that's what I'm going to be talking about next. This is a project with Steve Giddings and Seth Koren. There we go. Okay, so something that the description of black holes, well, our description of black holes came from general relativity, and it didn't include quantum mechanics in it. In fact, Stephen Hawking, 45 years ago now, 47 years ago, studying black holes, he found out that classical black holes, as they are described in general relativity, when you combine them with quantum fields around that region of spacetime, they radiate. They radiate thermal radiation, as I show in this picture. And in fact, the radiation increases as the size of the black hole decreases. So as it radiates away, it radiates some of its energy. So the size of the black hole gets smaller and smaller, and the temperature increases, meaning that it's going to radiate even faster. So this is a runaway phenomena that ends in a evaporation at the end, where the black hole is just gone. So that was the prediction of this very robust calculation by Hawking, and that created a problem. The problem is that this radiation has the same, it's the same regardless of how the black hole was formed. It doesn't care about how the black hole was formed in the beginning, but it only cares about the macroscopic properties, the mass and the size of the black hole. If you form one black hole by colliding a star, or if you form another black hole with the same mass by colliding a whole bunch of Britannica encyclopedia, the radiation that they emit is indistinguishable from each other. Now, why is this a problem? This is a problem because once the black hole evaporates, there's no remnant that is going to tell us where the information of each one of these collapses is going. Another way to say it, once the black hole is gone, all of the information that was inside of the black hole is also gone of our universe, and there's no trace in the radiation to recover that information. This is a very important problem with our tenets of physics, the way that we do physics, and we say that this loss of information from the universe violates unitarity, which is that given certain initial conditions, we can predict the state of our system for all future times. And this goes against the tenets of quantum mechanics. So consistency with quantum mechanics for the classical black holes, here I'm calling classical black holes, the original description of general relativity, requires modifications. And since this puzzle was introduced by Hawking in the last 47 years of a lot of study in that paradox, has suggested that the modifications that are needed could extend as long, not only at the center of the black hole, but it could be needed all the way to scales of the radius of the horizon. So the modifications could be as large as the horizon radius, and this is a big deviation from what we expect of black holes in general relativity. One important question in this project is, given this problem, is it true that the black holes that we see in nature, that we receive the gravitational waves that we observe through the Event Horizon Telescope, that is described as the black hole of general relativity, or are they different objects? And to be more concrete, how can we quantify the answer to this question using gravitational waves? How can we start parameterizing those deviations? Good. So here, one solution is to take the objects that we know as classical black holes and replace them with a new kind of object that has no horizon. The main issue of classical black holes was the existence of this horizon that would generate the radiation and would allow, would prevent any of the information inside to escape. So some of the proposals include getting rid of that description and include something that from the outside, it looks like a classical black hole, it behaves like it, so it follows our expectations, but the internal description is different. A couple of proposals have appeared throughout the years. These are what I call exotic proposals. There are some, the gravastars is one of them, the Planck stars have been proposed, fuzzballs, the idea of firewalls, that maybe something very dramatic is happening at the horizon. The problem with these proposals, even though each one of them give a prescription in which the information paradox would be resolved to a certain extent, is that they do not have a very concrete description that we could use to compare the data that we have from gravitational waves. Or at least it's not clear how you will start modeling the merger of some of these exotic objects. So it's going to be hard to falsify them right now using the data that we have from LIGO. So we want to offer a toy model that is going to behave as one of these. Sorry, let me just show my notation. These replacements to classical black holes, we call them compact quantum objects. Compact because there are a lot of mass in a very small region. So these are the CQOs. One sec. There we go. A first model for these quantum compact objects would be a neutron star. The problem with neutron stars is that the ones that we know how to model them, they do not have the masses that we see in the mergers at LIGO. So I mentioned that LIGO can see the mergers of black holes of order of 30 solar masses. Neutron stars do not go beyond 2 solar masses, roughly. So they're not as massive as we want them, but they offer a first an idea of how we can start parameterizing a different object from a black hole, and that is by using an effective stress tensor. In particular, we're going to be using an effective stress tensor with an effective equation of state for a perfect fluid. This is a simpler model that already has some important features, as I will show, for which we can start looking at these parameterizations. Okay, these models, if they can give the relevant masses that we observe already at LIGO, are going to offer these alternative scenarios in which we can start checking whether LIGO can already distinguish them or whether these are still possible descriptions just to parameterize how much we don't know yet. We are not proposing that these are real physical objects out there, but these are a toy model where we could use them to get some quantification. So our toy model, I will explain next, is a perfect fluid star in general relativity. That would be the effective stress tensor. Okay, so toy model, we propose a spherically symmetric and static stress energy tensor with two pieces. At the core, in the inside, we're going to be using what is known as the stiffest equation of state. That is the equation of state, this relationship between pressure and density, mass density, that has a speed of sound marginally below the speed of light. In fact, by stiffest, we mean that the speed of sound here is the speed of light. It doesn't go beyond that. We don't want to have any bad properties that would already disqualify these toy models. So for the core, we propose this equation of state. And the problem is that this equation of state has a very sharp edge where you have the density I'm going to show in the next plot, and it just goes to 0 right away. So that discontinuity creates some problems when you're trying to do numerical simulations, or it is going to require some additions of some boundary stress tensors if you want to have them as modeling the gravitational waves. So to get rid of that roughness in the corner at the surface, we add a polytropic tail that very quickly interpolates from the edge of the core all the way to 0 density in a smooth way. This is the form of a polytropic tail. Here, rho naught, it's a cutoff density. K and gamma are determined by just declaring that the boundary conditions of the tail are smoothly connected, both to the core and to zero. And finally, here A and B, A is going to determine the central density of our model. So you can change the central density, which in turn is going to change the mass of the object. Together with B, B is going to tell us at which density we end up the core, and we just attach the polytropic tail. Both of these together, A and B, are the two parameters that control both the mass, the radius, and implicitly the compactness of the object, which is just how much mass you can fit in a given radius in this ratio. These are the equation of states. This is a plot of the model. In red, for example, I'm choosing one value of A. This is a plot of mass density or energy density here as a function of radius. And at the beginning here, the value of A is going to determine what is the central density. And then in red, you can see the stiffest equation of state just going down all the way to the value of our cutoff density. Now here, you will have the sharp drop-off. So we have attached, before we reach this drop-off, many different polytropic tails, and all of these are for different values of B. And of course, if you want to change the value of A, you're going to get another plot of this. All right, so we have a parametric space with A and B. Oh, 1 second. Here we go.
Excuse me, Gabriel.
Yes.
Is rho naught another parameter? Or
yes. This is the cutoff density. Oh, let me see if I. Which I think we. Yes, it is an extra parameter for which we can use physical input to choose the value of it. I'm forgetting right now what is usually the one that is used. It's the oh man, I'm blanking on it, but it is an extra parameter that usually just fixes here the units in which you're measuring rho to a minimal cutoff here.
okay.
Yes. It is extra. I'm forgetting right now the details for that. Okay, so for this toy model, we have two parameters. Once we fix rho naught, we have A and B, that A and B are gonna change the mass and the radius in the units that we use with rho naught for these objects. Okay, a couple of features. By choosing, there's a corner here, down here, of parameter space in which, okay, what I'm plotting here as a function of A and B, that's where I should start. That's the compactness of the object, which is the ratio of the total mass by the size of the object, all the way at the end of the polytropic tail. And why is this important? This is important because black holes are very compact objects. The compactness for a black hole is 1/2. And we want to get as close as possible to that compactness to recreate the gravitational wave that will be emitted in the merger, which is very sensitive of the compactness of the two objects that are merging together. In particular, a characteristic feature that is going to drive how the wave that you get emitted looks like is whether your object has a light ring. A light ring is created only when your object is more compact than 1/3. So in particular, we are interested in this corner here where we find compactnesses. The more beige the color, the more compact the object is. And below this green line, we have all of these regions of parameter space for which compactness is greater than 1/3. And not only that, but we also want the region where our toy model passes a first check of stability. In this case, linear stability, the mass with respect of the central density. And that region is inside of this corner in red. So there's here our sweet spot where we're looking at these objects that are stable in this condition and they are ultra compact, or they have a compactness greater than 1/3. Okay, so given this toy model, how can we compare with data in LIGO? What LIGO is looking at is you have two objects, in principle, two black holes. This is the proposed objects, they are rotating around each other, and they are going to merge and form a bigger object at the end. This is not a bigger black hole at the end. This can be divided in 3 phases. First, we have the in-spiral, where each one of them is rotating around the gravitational potential created by the other one and themselves. As they get closer to each other, they start to getting more and more distorted. And there's a rapid plunge and merger where they just get closer to each other, a horizon appears, and they just form the final black hole. But because there was this collision, there's the final ring down, which is when the newly formed black hole stabilizes from being perturbed to just reaching its final configuration. We are interested in the first phase, the in-spiral, which is where you can do an expansion in what is called parametric post-Newtonian expansion, which allows you to have some theoretical control on what this signal is going to look like. If you want to analyze plunge and merger here, you need full numerical relativity, which we didn't have access to yet. And there's also the possibility to look at the final perturbation of the final object. We are not going to be using that here. We are constrained here to this tidal love number. Okay, so a couple of equations. The important parameter here is that it is known as the tidal love number. So when you are in the spiral, given the presence of the other object that is generating a tidal field, a gravitational tidal field, the first object is going to get distorted. And that distortion is parameterized by this quadrupole moment, which is linear on the tidal field epsilon. It involves its size, but this constant here, the k sub 2, is known as the tidal love number, which is a dimensionless quantity that encodes information about the internal structure of the object, basically how bendable it is in the presence of the other tidal field. This tidal love number, which is a dimensionless quantity, is constrained by data in advanced LIGO. So at design sensitivity, we expect, people at LIGO expect that this number can be constrained up to order of 100. So if it is lower than 100, they cannot distinguish the value of k. And this is true for a broad range of masses. And the surprise here, or the key element for this analysis, is that for a classical black hole, K2 vanishes. This is a result that was found in 2016 by Porto, and then Porto found it for static spherically symmetric black holes. And then this analysis has been extended to rotating black holes, to linear order in spin. And I think there's an additional analysis in second order in spin, that the K2 value for a classical black hole vanishes. That means that data in LIGO cannot distinguish values of K2 between 0, which would be a classical black hole, and 100. So now we look at our toy models. We compute the K2, which has to do with the compactness of our objects and the equation of state that we are using. Here are the values that I'm plotting. Notice that even the beige color over here, these are values of 16, way below the 100. And in fact, in our region of interest, in this parameter space, the values of this love number is from 2 to 6. So here, the conclusion is LIGO at current sensitivity is not yet able to distinguish between classical black holes and what would be these toy models that will have a different internal structure. To start distinguish them, we would need bigger interferometers, not 4 kilometers long, but actual longer interferometers. One proposed one is known as LISA, which puts interferometers in space. The size of the arms through which they shoot the lasers, it's almost 100 times the distance from Earth and the Moon. And this interferometer is expected to reduce the sensitivity or the precision of K2, the love number, up to 2 orders of magnitude. So that is going to already start distinguishing whether it's closer to 0 or it could have some different features at large compactnesses. Finally, of course, if we had access to full numerical simulations of this toy model, we will also be able to start seeing if there's any deviation at the plunge, the region where there's not a lot of control theoretically, but you need full numerical simulations. Okay, should I stop?
Sorry,
yes.
If I could stop before you go on.
Yes.
So when you started talking about these compact quantum objects, you said they, neutron stars wouldn't work because they don't have masses big enough to represent the objects that LIGO sees. And then when you talked about your model, you were only talking about the compactness. So is there a scaling symmetry which lets your objects have arbitrarily large masses so that you can get masses of 30 or 50 solar masses?
Yes. In fact, we do explain in our paper, there's a virtue of this toy model that I didn't include here, which is that we do have the additional scale symmetry where you can get arbitrarily large masses. So this toy model gives you any range of masses, so you can tune it at the masses that you see at LIGO to make the comparison more precise. Now, I think that extra parameter is associated to rho naught, but I don't remember the exact formula. But you're right, there's that additional feature of it.
Okay, thank you.
Okay, now I want to change gears. I'm gonna introduce the ideas of holography.
Gabriel,
yes.
Sorry, maybe before you change gears, let me ask a question about this. So I recall that LIGO saw some events involving neutron stars, and if I understand, and maybe you go back one page, or two. I think they wouldn't have the limit of k equals 0, right? Because they're not going to have that, not like a classical black hole. Is there anything that could be learned about the model, this toy model, if you could map it onto neutron stars that might be in the range of LIGO? You said that their masses are not big enough. Maybe the right way to phrase my question is, how big would it have to be, and how far away are the recent observations that LIGO has of neutron star collisions?
Yes. Let me see, what can I say about that? The particular value of K2 is something that depends a lot in the equation of state that you're using to model your objects. If you use the very complex equation of states that I don't have a lot of knowledge about those for neutron stars, you're going to get predictions for different values of K2. You're right that we could start using that if let me see. I'm not sure if your question was how to use the connection with neutron stars to this toy model, because I think some of the features that they observe in LIGO that they know that comes from a neutron star, there are other features that already tell them that these are going to be not black holes. So they don't expect them to be classical black holes. So there are like larger reasons to believe that these are neutron stars and not what are classical black holes. So that will rule out already the use of this model.
I see, because really it's not going to match the model in terms of the density. Okay, right. So yeah, actually, maybe a reasonable follow-up question is I suppose the things that rule it, that distinguish it from that is really not the first phase that you're studying here, but the other phases, the merger and the ring down phase, right?
That's also right, because a lot of how the merger, and that's this region in between, a lot of how this merger is going to look like, it's heavily influenced by the presence of the light ring. The light ring acts as a big, what's the word? It obscures the signal a lot. A lot of the interaction that is happening inside of the merger gets finds itself being inside of the newly formed horizon, so it doesn't even escape. And some of that feature, when you have neutron stars, actually manage to escape. So I think even from this piece, you can already rule out that these collisions would be black holes. And we want to work in the signals where we expect them to be black holes, and we want to see if there's anything else that we could use to rule them out.
Right. Okay. Yeah. Clearly, just it's just not. It's different from the model. It's not applicable. That makes a lot of sense. Thanks.
Right. Good. Okay. Okay. I'm gonna try to speed up a little bit. Okay, now going to changing gears, talking a little bit more about this concept of holography. As we discussed before, there are some problems with black holes and this known information paradox, which is information gets lost, that we need to fix. Also, we would like to know what happens, for example, in the first moments of the Big Bang. This is a region of the universe, a period of the universe, where the energy density was so close to each other, so dense, that some of the predictions from general relativity we don't believe are going to be accurate. So we need to include quantum mechanics into the equation. And more generally, we want to reconcile some of the principles of quantum mechanics with gravity, and to do that, gain further insight into how the universe works. So that's why we're looking for a theory of quantum gravity. A hint that we had early on was, first of all, from Hawking radiation. Black holes radiate. We know that black holes can be assigned a temperature that is proportional to its surface gravity. But not only that, this analogy of having a so-called temperature was made more robust with ideas of Bekenstein that also assign an entropy to the black holes. Entropy is, in physics, we use it as a measure of how much information is can be stored in a particular region. So if I give you the entropy of a particular volume, that is telling you how much information can be stored in some sort in that volumetric region. What Bekenstein found is that for black holes, the entropy it is not proportional to the volume of a black hole, but it's proportional to the area of the black hole. Now, this was surprising, and de Hooft and Susskind came later to propose that in a theory with gravity, the presence of black holes, even tiny black holes, they necessarily create a cutoff in your theory, which means if you look at a particular region of space-time and you want to put as much information as densely packed as you can, eventually you're going to have a lot of energy in that region that you're going to create a black hole. And the black hole is going to give you a cutoff because you're not going to be able to introduce more information than the one given by the entropy of the area of that region. So in a sense, we have this property known as a hologram, which says that the region in a particular the information in a particular three-dimensional region can be encoded, fully encoded in its surface, in a two-dimensional surface, kind of like the way we have holograms in a two-dimensional surface. Okay, this idea was made concrete 24 years ago by Maldacena, who taught us that there are dualities between theories with gravity and without gravity. This is what we call the gauge-gravity duality. He provided a concrete example, an equivalence between a theory of full quantum gravity, a string theory, that these are some words, it's compactified on an ADS5 S5 geometry. But this is just to show this a particular geometry that we know as ADS. And on the boundary, the dual theory, the one without gravity, is a particular class of gauge theories that enjoys a conformal symmetry. So these are known as conformal field theories, or CFT. And this is how we come with an ADS-CFT duality or correspondence between a theory with gravity and one without gravity. The reason this is an example of holography is that the quantum gravity theory lives on a d+1 dimensional space, and the CFT, we always think of it as living on the boundary of that theory in a one lower dimension. And they are supposed to encode the same information of your system. Okay, now this is one picture that gets shown. I've seen a couple of times when you talk about ADS-CFT in the interior of the universe. You can have black holes, you have superstrings, and on the boundary you have your conformal fields, your radiation. But maybe a more friendly picture I like is this one. One of the common pictures is imagine a can of soup. I chose to imagine a kind of SpaghettiOs in which the properties of these of the inside, the flavor, the texture, and all of that is inside can be encoded in the label in a two-dimensional surface. Now it's going to have different. It's going to be encoded in a different language, right? Here you have the actual pasta, and here you might have the ingredients that you might need. A theory tells you how you put together the ingredients to learn properties of the interior, and you can go back and forth. All right, so finally, I want to talk about a project within holography with Gary Horowitz, Sergio, and the Andean, my fellow grad students. Okay, so in this holographic duality on the boundary, we have a quantum field theory. And this is a quantum theory for which a very fundamental property is that it is required to be causal. What that means is that when you compute a commutator of operators in your theory, and you evaluate of two local operators at space-like separated points, we demand that commutator to vanish. This is what provides us with causality of the theory. And given the duality, we expect the bulk theory to reproduce this property, this boundary causality. Classically, this is true because spacetimes, it was proven by Gao and Wald. This is the Gao-Wald theorem that spacetime that satisfy the null energy condition, which is a condition that we expect reasonable spacetimes are going to satisfy. It is ensured that the fastest way between 2 points on the boundary travels that stays on the boundary. So it is not possible to go faster through the bulk. Semi-classically, there's another condition that also is going to ensure boundary causality. That is the acoronal average null energy condition. And I think it was Wald that proved that semi-classically, the generalized second law implies this condition. So in general, we expect this also to guarantee boundary causality in the many examples that we use. The problem is that when you go to a non-perturbative bulk approach, in which we use a full path integral of the fields in the bulk. In here, we do the path integral over metrics in the bulk and also over matter fields in the bulk. We generically expect a problem. So let me explain what this puzzle is. Well, the way we do the non-perturbative is by fixing boundary conditions and then integrating over all possible fields in the bulk that satisfy those boundary conditions in our path integral. Generically, some of the metrics that go into this integral are going to violate boundary causality. That means that they offer a path through the bulk that connects two space in the boundary faster than it would be done on the boundary, right? You can just take a shortcut through the bulk. And if you compute the commutator of two bulk fields using these particular metrics, you're going to get something that is non-zero. They're causally connected in the interior. Why is this a problem? This is a problem because in your integral, all the metrics that satisfy boundary causality are going to give you a 0 here. And then you have all the ones that violate that are going to give you non-zero answers. And we expect this full integral to give us the 0 that we are expecting from the boundary perspective. Now, it is possible that there could be, okay, so how do we 0? Before I say that, let me just mention that these metrics that violate boundary causality, some of them, many of them, in fact, they don't have any other pathological properties. These are well-behaved, low curvature metrics, so, and they don't have any causal pathologies that by themselves would tell us that we need to exclude them from the path integral. There's no real reason to exclude them. So the question is, how do we get 0 from this calculation? Perhaps there's some cancellation. Sometimes non-zero pieces of your integrand cancel each other. This is possible, but we believe this is highly unlikely because it's not only one integral that needs to vanish, this one of the commutator, but in fact, any operator for any bulk field that we want to multiply to the operator inside of the integral of the path integral should also vanish from the boundary perspective. So we have a collection, potentially an infinite number of different integrands with the same measure that need to vanish. So we think this is highly unlikely to happen. And in fact, we provide a solution that involves looking a bit more carefully at the choice of boundary conditions that is going to resolve this problem without having to show that there was any weird cancellation happening inside of the integral. So it's going to be a more satisfying solution. Here, I wanted to offer some examples of these metrics. This is a very simple example. Is static spherically symmetric. F is a function of B, for example. This is a family of metrics. If you compute what is the time that it takes to go from boundary to boundary through a radial geodesic, the condition for that metric to violate boundary causality is that that time that I'm calling here infinite, T infinite or T boundary, to be lower or faster than the time that it takes through ADS, in this case, pi in units of ADS radius. All we need to do that is to choose the function B, F here, to be greater than F for ADS everywhere. And this is one sufficient condition to show that this bound can be easily violated without any pathologies. In fact, well, I already mentioned that these are well behaved. There's no closed time-like curves, low curvature. But also, whenever you find one of these metrics for which boundary causality is violated, meaning that there are 2 points that are time-like connected, you can perturb the geodesic that is connecting them. And all of those deviations are also going to be causally connected. So there's an open set of metrics that violate boundary causality. Okay, now the dictionaries in holography, I mentioned that holography offers this duality between a gravitational theory in the bulk and a theory without gravity on the boundary. How are they connected? How can I go back and forth? The more general statement is that the partition functions of both theories are equivalent to each other. Here I have the bulk with respect to some bulk fields, and here in the boundary, these are given by sources. So the bulk partition function is computed through a gravitational path integral, where we are fixing the boundary conditions on that gravitational path integral, the values of the fields and the metric field in the boundary. For the boundary partition function, we are introducing some sources of local operators in the boundary, and we are integrating not over metrics, but in the metric that we are selecting, that we are fixing as the boundary condition. Good. So given these two partition functions, how do we compute one of the most basic objects of your theory, a correlator? In the boundary, a boundary correlator is the expectation value of n number of local operators inserted at different points. The way that we will get it would be by using the partition function as a generating function. But because the boundary partition function is supposed to be equivalent to the bulk partition function, we expect to get this correlator in the boundary by taking partial derivatives with respect to the sources of the bulk partition function. There's another way to compute. This is known as the extrapolate dictionary, which also gives you the same correlator. And this alternative way is to first compute the correlation function using the bulk fields associated to the fields that you have here as sources, and taking the limit of this correlator to go to infinity, matching the point that you have in the boundary. And all of this, you do it inside of a gravitational path integral, where you are integrating over all possible metrics that match your boundary conditions. Here we can see in the second dictionary, in the extrapolate dictionary, that the problem is more acute. That is, sorry, the way that we will phrase our problem in the extrapolate dictionary is, if we compute the 2-point function, the commutator for each one of the metrics, and then we take the limit, we expect this to give us 0, but we still haven't answered how we deal with the non-zero answers, the one for the metrics that are violating boundary causality. Okay, so we need to look into what the commutator is. So here G means that we are doing this expectation value of the commutator for an individual bulk metric G. What you need to do is you need to take the difference of two 2-point functions with the point insertions being flipped. The problem is that the way we compute this is through a path integral but the path integral always computes what is known as a time order correlator. So you're evolving from a certain initial condition, and you first pick the first point that appears to you, and then you go to the next point in time. They are time order. So the way, for example, if Q happens to be to the future of P, so first appears P and then Q, your path integral is first going to pick the value of P and then Q. So this correlation function would be already time order. But how do we compute one that is out of time order, where Q appears first? This is the out of time order. And the answer is that we need something known as a time flow. I'm going to show you a picture in a moment, but basically it means that you choose your spacetime such that you evolve first in a sheet until you reach the second point, and then you evolve backwards to collect the first point, and then you evolve forwards again. But let me show you the image. Okay. So if you are computing the correlation function of 2 points that are already time order, you just do a normal path integral where the path integral is evolving you first to P and then to Q and then to later times. But when you want to compute the out of time order correlation function, you need to introduce this time fold, which is these additional sheets of spacetime, first such that there's no insertion of the P point in the first one. You evolve forward until you reach the point Q, and then you evolve backwards using U dagger, and then you evolve forward again. These in general, generically are different. They don't have to be equivalent to each other. Okay, so given that now we have this, we have learned that we need to introduce time folds to compute the commutator. How do we fix our original problem? Well, we need to update our dictionary, which says not only the partition functions are supposed to be equal to each other, but we have to make sure that the boundary condition, including the time fold that we choose on one side, for example, here on the boundary, needs to match the boundary condition on the other side. Another way to say is that if we have to include a time fold on the boundary calculation, we must include it also as a boundary condition for the bulk calculation. If we do not have to include it, we must avoid a time fold in the bulk calculation. Now, a small problem or a small detail is that the boundary theory, we are assuming that is a theory that is causal and unitary. As a QFT, we assume that is unitary. And we know that the gravitational path integral, if it calculates unitary evolution, you can always go to a particular point, evolve to a particular point, and you can keep evolving forwards and backwards, and those two pieces of sheets are going to cancel out each other. So you have a freedom to choose how much you want to evolve forwards, backwards, and then as long as you reach your initial final condition, you have this freedom inside from the boundary perspective. The problem is that from the bulk perspective, we don't know that the gravitational path integral describes unitary evolution. So we cannot use this freedom. We are trying to bypass this idea because we don't have this description. So we introduce what is known as the minimal time fold, and it has two pieces. The first one is that we are only going to introduce a time fold whenever it's strictly needed. So if we have 2 points that are time-like order, and that's the correlation that we are computing, we shouldn't introduce any extra baggage, any extra time folds that are not going to add anything to the calculation. The second piece is that when we are connecting 2 points, when there's a need for a time fold, the time fold should be very economical. We should reach from one point to the other one and then backwards. We should not evolve further to the future or further to the past. And this is what we say here, that it needs to sweep only causal diamonds between the insertions. In fact, I will show in the last slides how this is enough. Let me show you this picture again. These time folds actually were minimal time folds already. If you have 2 points that are in the order that you want to compute it, you do not introduce any extra baggage, any extra time fold. You just use one piece of spacetime. If you have 2 points that you need to compute the out of time order correlation, you are going to introduce a time fold, but you do not go any further or any backwards, further backwards than you need to do. Okay, now why is this enough to resolve our puzzle? I mentioned 2 different dictionaries, so I'm gonna show how the puzzle is resolved in both dictionaries. From the perspective of the differentiate dictionary, I have updated this differentiation of the partition function to include the timefold f here in the bulk partition function, where f is a minimal timefold. If x and y are space-like separated, I mean, if we imagine this for 2-point functions, the minimal timefold in both cases is a trivial one. There's no need for a timefold. Therefore, the difference between the two correlators is going to be the same since there was no timefold added. I guess the extra piece is that the partial derivatives with respect to the fields, they're going to commute. So after this after you commute one of them, you will find the two of them being exactly the same with the same timefold. If they are causally connected, 2 points on the boundary causally connected, so you have to introduce a timefold. You only introduce it for the out of time order correlation piece of the commutator. So when you get the difference between them, even though the partials commute, now one of the terms is going to have a different timefold, so the difference is not going to be zero generically. It can be non-zero. All right, so what about the extrapolate dictionary? We had this problem that for two space-like separated points in the boundary, there are metrics in the bulk for which they are causally related. So generically, these are going to be different when you compute them in different timefolds. So this is where you get the non-zero contribution in the original puzzle. However, we are integrating over more bulk metrics that satisfy our boundary conditions. If these points are space-like separated on the boundary, you do not need to introduce any timefolds on the boundary. So there's no need to introduce any timefolds in the bulk, because if you introduce them, when you take the limit, you're going to end up with a timefold on the boundary, and you're violating the boundary condition that you're using in your path integral. So non-trivial timefolds in the bulk are not allowed for each of the metrics in the bulk. What this means is that using the same trivial timefold for the 2 points, these two commutators, the time order and the out of time order, are all going to be the same, using the same timefold. So they're going to be equivalent for each metric, and you're going to see the cancellation in each one of the metrics inside of the path integral. So this was just using this freedom that we found in the boundary conditions, because we are assuming causality and unitarity of the boundary that allows us to revisit how we are doing the path integral and get rid of this puzzle. Okay, now I'm running out of time, but that's good. I just barely, I mean, this has been a very interesting set of projects. I think I've explored just a few corners, and I hope you get to see that there are many, many more interesting pieces in spacetime. I talked about gravitational waves and how we can already start parameterizing how the data from LIGO is telling us whether the objects that are out there in the universe colliding are black holes as described as general relativity, or how they could be different. And finally, in this, within the context of holography, we saw that including causality violating metrics, they first created a puzzle, but with the right analysis of boundary conditions, we see that there's no puzzle at the end. And it will be interesting to see what kind of effect these boundary causality violating metrics would have in the theory. So with that being said, I want to thank first my advisor, Gary Horowitz, for these wonderful 6 years. I want to thank my collaborators, Seth Corren, the Indian one, Sergio Hernandez, and Steve Giddings, for very interesting projects. My professors, my committee, David and Shim. And of course, finally, I want to thank my friends and family for supporting me throughout all this time. Thank you.
Okay, thank you very much, Gabriel. So I guess now we have a little time for questions from anybody in the audience. So let's open it up. If you have a question you want to ask about this talk, just unmute yourself and speak up. Okay, if there are no questions from the general audience, I guess then we should excuse the audience